Swayam Prabha. Digital India. Educated India.
This maritime engineering, as you see, is a very special program which has got multidisciplinary input from mechanical, civil, structural, aerospace, naval architecture, chemical engineering, electrical, electronics, applied mechanics. It's a multidisciplinary program. You will find this program is completely different, dedicated to industrial training and thorough capacity building on the new trade of maritime sector. It's a grooming economy which will give you a lot of job opportunities and research frontiers as far as India is growing. And the Blue Corridor effect, which is planned by Government of India, is one of the important mission which requires maritime engineering growth to happen in the country. So this program caters to expected that capacity building in this program.
Friends, this is part of a material science engineering laboratory which becomes one of the teaching aid for the maritime engineering program. So when you talk about materials innovation in maritime industry, though concrete and steel have been conventional candidates of choice for engineers, for example, we have titanium vessels, high-speed craft boats made of fiberglass. These are all advanced materials which actually do not come across conventional standard design code of practices. We conduct box furnace test, tube furnace test, vacuum arc melting, induction melting, vacuum induction melting, vacuum sealing unit, which are all present in this laboratory as a small segment of material science laboratory. Friends, a typical furnace where the operating temperature for testing specimen can go as high as 12 degrees Celsius. Generally at room temperatures and ambient condition, the mechanical properties will not alter much. As you see in the course lectures, you will notice that strength of the material get degraded when the temperature rises beyond 600. Therefore, when you talk about fire resistant design, you must also choose an alloying element such a manner that the strength doesn't degrade beyond 600 degrees Celsius at all. Welcome to the ambience of IIT Gandhinagar lecture theatre. This is one of the interesting classrooms where the maritime engineering classes will be conducted. We have got state-of-the-art projection facility and good audio-visual recording systems. Once the lecture is over, you see the system here. We can generate the PDF files of the lecture directly and you can email the PDF files directly to your email IDs. So it's a state-of-the-art facility we have in IIT Gandhinagar where the lectures are lifetime recorded and shared with the students immediately. This is the IIT Gandhinagar library. This has got all collections of books which are referred as the standard textbooks and references for the course and the program. It also has lot of online editions of design code of practices and reference materials and e-collections of various video lectures of international courses and programs related to maritime engineering. We will be taking you around to the advanced material manufacturing units. So you will have state-of-the-art facilities available at IIT Gandhinagar. So welcome to the program to join MTech and PhD at IIT Gandhinagar Maritime Engineering. So please try to enjoy and take the advantage of this to the maximum. Welcome to the program and welcome to IIT Gandhinagar. Friends, welcome to the 8th lecture on the course Marine Renewable Energy Systems, where we are discussing about the analysis, design and development of renewable energy systems in general, but with a principal focus to wave energy converters and offshore wind turbines. So in the last lecture, we discussed about the preliminary design of wave energy converter in frequency domain approach. So in lecture 8, we will talk about the primary design parameters that control the development of wave energy converters. So if you look back the previous lecture, we said that the amplitude in a complex form after analyzing from the frequency domain is given by this equation, which is F hat E omega by minus omega square m plus am, additional mass or added mass, plus the restoring force, the hydrostatic force, the restoring force of the power takeoff mechanism as one segment, plus I omega of the damping arising from radiation damping of the PTO and the damping of the PTO itself. Let us call this equation as 1 for this specific lecture, but do not continue this number with what we have in the previous lectures. Okay? So, we are having a local number, so it is easy for us to refer back to the same lecture, but when you look them in a continuous order, then you got to look at the equation, not at the number carefully. Okay? So, now we said that in frequency domain approach, we will be able to obtain the complex amplitude of the wave energy converter. So, x hat omega is the complex amplitude of the response of the proposed wave energy converter, which is modeled in frequency domain approach. Suppose if the diameter of the device, what we call as an effective length of interaction. So, let us say the diameter of the device, which is otherwise referred as effective length of the device with respect to the incoming wave. Usually, this is applicable in case of non-circular sections. If it is a circular section, we go for diameter. If the diameter of the device is greater than, let us say, about 15% of the wavelength, then literature say that the Morrison equation applicable to this analysis is no longer valid. Okay? And in such cases, forces are estimated using linear diffraction theory. And Frau-Krelov method. Okay? Now, if the diameter of the device is extremely large, what happens physically? If the diameter of the device is very large compared to the wavelength, then scattering of the waves occurs. Now, this increases the importance of diffraction force. Therefore, friends, if T by L, where D is the diameter of the device, L is actually the wavelength. If d by L is greater than 1, okay, that is the diameter is much larger compared to the wavelength, then it will lead to a pure reflection scenario. Okay. So, in wave energy converter designs, generally incoming waves which exerts force on the device, and that is dominant by Froude-Kellogg forces, okay, and the rest comes from diffraction. So, the primary force component comes from the Froude-Kellogg force, and the balance comes from diffraction force. Okay. We also said that in frequency domain approach, when you start analyzing numerically a problem, then we get an output called response amplitude operator. Essentially, it is a transfer function. Which represents the motion characteristics of the device. Okay. This actually represents the motion or the response characteristics. Of the device. It also helps us to understand the C state condition with respect to the response characteristics. So, it means it also helps us to map the dominating frequencies which excites WEC maximum. So, our objective is to harness the maximum power, to absorb the maximum power. So, now response amplitude operator is actually the ratio of response amplitude of the device which is measured in x to the wave amplitude. So, mathematically this can be said as x by Na, where Na or eta A represents the wave amplitude. Now, from the previous equation, we already know the complex quantity of the response. Let me write that equation for you. We already know x of t is R e, the complex quantity of this E I omega t, we take only the real part. This equation was already given and explained in the previous lecture. So, once I know this complex quantity, then I can able to find out the response amplitude easily once the compressed quantity is known to us. Now, the peak amplitude of raw response amplitude operator usually is designed to be greater than the WEC's raw, so that it can resonate. And that is where we are working for the maximum efficiency. However, in multi-body dynamics, the peaks can occur at various frequencies. Therefore, if we want to really find out the maximum absorption of energy, we should then decide this for a wide range of frequencies. In that condition, the phase term of the complex raw becomes important. Because the phase difference between the motion of the WEC and the instant wave is captured in this term. Okay. So, to optimize the WEC design, the response amplitude should be maximized to in that case, the ideal design could be keep WEC and the incident wave in same phase as far as velocity is concerned. So, therefore, the maximization is usually done by passive controlling this. So, we have to choose the PTO parameters, that is the stiffness and the damping coefficient, to estimate the optimal values for which the response in turn gives me the maximum. So, this will lead to or initiate maximum response of the device. Friends, this particular idea is actually a reverse concept as far as design of structures is concerned. There we do not want the structure to resonate at all, but here we want the system to resonate, but that is where I can harness the maximum energy. So, therefore, friends, if I have a 0 phase difference, if we have a 0 phase difference by some design, let us say by some design methodology, 0 phase difference, then to achieve the maximum harness of power, one need to use active external control So friends, this is where the design of WEC gets different from different approaches of design. Okay. So either we do passive controlling to maximize the absorption capacity. This is true only when the WEC and the incident wave are in same velocity, same phase in the velocity, so we can do this. If they have zero phase difference, then we have to use active control mechanism to achieve this. So this is generally modeled and assessed in time domain due to the non-linearities. So in frequency domain, this cannot be correctly addressed. Now let us come to the argument of calculation of PTO force. PTO force can be assessed by imposing a damping value to PTO. So I should put here a condition called virtual damping. This is not the real damping to be put on the PTO. So I put a virtual damping to harness the maximum power and I apply this virtual damping number to PTO. Once this is done, then the PTO stiffness is tuned to the device based on wave periods, so based on the wave period, we tune the PTO stiffness. Unfortunately, friends, commercial packages do not allow us to have a provision to incorporate something called virtual PTO stiffness values. Therefore, only damping coefficient should be used to calculate the PTO force. And in turn, we get the absorbed power. Okay. So depending upon the configuration of the device, the representation of virtual PTO changes the system. So that's the catch here. The virtual PTO design actually alters the proposed geometric design of the WEC. And this is a very important outcome we learned. We obtain from the frequency domain approach. Suppose if we have a wave energy system with rotational motion, let us say wave energy system with rotational degree of freedom as an active degree of freedom for harness. Suppose we have a design like rotational motion is being active, maybe pitching or rolling, then instead of PTO damping, one can use hinges at PTO connection And by tuning these hinges, PTO design can be controlled. Therefore, the external forces what the PTO receives is calculated at the provided hinge. The rotational damping term is converted to equivalent linear damping with reference to the PTO's virtual system, and that is how the WEC is designed. Okay. For example, if the spring converts the kinetic to potential energy, and vice versa, without absorption or any dissipation of energy. Of course, friends, in this whole discussion, heat loss is neglected. Therefore, in such situation, the only contributor which comes for the design of WEC is the damper. Hence, the only contributor to the WEC design is the damper. Therefore, I can now write an equation of absorbed power. Power absorbed by the wave energy converter, which is expressed as PA, is given as PA is equal to 1 over T of 0 to T of the damping coefficient of PTO velocity square dt, which is now equal to half CPTO omega square mod value of x omega square. Call this equation number 2. Therefore, a wide range of PTO damping values are considered to maximize the absorbed power, right. So, the absorbed power now depends on the damping ratio of PTO. So, you keep on considering wide range of damping coefficients to maximize the absorbed power, and the corresponding power values are estimated. Then an envelope is drawn. So, consider a wide range of CPT to maximize PA. Then develop an envelope showing power absorption at various damping values and frequencies. In case of irregular waves, the output will be in the form of spectral density function referred to as response spectrum. So, in case of irregular wave input, the output will be the output of the device will be expressed in form of response spectrum. And the area under this spectrum gives the absorbed power, which is estimated for different CPTO values. Therefore, frequency domain approach gives only a rough estimate of optimal PTO damping, which is required to design the wave energy converter for maximum power absorption. So, if you have many devices, then we can use an index to compare them and find out which will be the better one. So, the comparison will be based on between different devices, will be based on the range of frequencies used to harness power. It is not the maximum power being considered, it is the range of frequencies being used. So, wider range of frequency used in power absorption is a better design. So, friends, it is not the amplitude which is seen here, it is the range of frequency, the x-axis values are referred. Okay. Therefore, friends, this type of analysis has its own limitation in terms of incompetence in representing non-linearities. Let us say the limitations of the preliminary analysis of WEC design done in frequency domain approach. The foremost limitation is incompetence to represent non-linearities non-linearities arise from the equation of motion itself. This is number one. Secondly, the real power takeoff mechanism and the dedicated active control systems to achieve the maximum power absorption cannot be incorporated in this approach. Therefore, an efficient design of WEC cannot be done only in frequency domain approach. It needs a continuation of this transfer to other medium. Let us see what is that. The major constraint why this happens is that in the whole analogy, we assume that the properties are linear. Superposition principle in the linear frequency will not be valid when non-linearities dominate the system behavior. Then therefore, friends, we need to leap over to time domain approach. Friends, let us see the summary what we have seen in this lecture so far. We have understood the design parameters, which are necessary for the WEC primary or preliminary design. We have understood the limitations of using frequency domain approach for WEC analysis. Then we ultimately said we take it over to time domain approach. Friends, generally in structural dynamics, frequency domain and time domain used to be complemented each other, whereas in WEC design, interestingly friends, they are not complementary, they are actually on a chain. You first do the preliminary analysis using frequency domain approach, then do the final analysis using time domain approach. So, both are necessary, they are not complementing each other, both are necessary in this case. So, possibly this is one of the system designs where I use both the approaches to arrive at the design. This is what we understand as a summary from this lecture. Stay connected in the further lectures to understand more about the design in time domain modeling and then how to take it forward to actually design the parameter for a novel wave energy converter. Once we understand this, then we will apply these concepts to various example problems and see how a WEC has been designed, developed, tested, modified and optimized for a given C state, especially for Indian scenario. Okay. Thank you friends. I hope you will enjoy the contents of the lectures. Please go through all of them in a continuous model so that you will get the whole of the whole content of the lectures instead of seeing part and parcel of them for your interest. Thank you very much. Stay connected. Namaste.